All right, in part one, we addressed how we're going to find the exact area beneath the graph of a function. And at the time, the functions and their graphs were entirely above the x-axis. Well, what we're going to look at now is the question, what if the graph of the function goes below the x-axis? How do we then interpret that definite integral as area beneath the curve? Okay, so we're going to look at graphs here as an example that kind of dips below the x-axis over the interval from a to b. So this could be any function. We just have one representative sketched here. And what we're going to start with, very briefly, just to see where we'll kind of refine this idea of what we'll call net signed area, is let's try to do this with a rectangular approximation. Now, you have two little regions there. You have that kind of upper part above the x-axis, and then that small part below the x-axis. If you were to look at a rectangular approximation for the part above the x-axis, your rectangle goes from the x-axis and hits the graph. And from the x-axis, since the graph is above, we draw upwards with our rectangle, so it looks oriented like that. So let's say that was an endpoint, x sub 1. The height would be determined by f of x sub 1, which, since that function is above the x-axis there, that function value, f of x sub 1, is positive. Multiply that by the width. A positive height times a positive width gives positive area. In fact, I'm positive. All right, now what happens if you take a look at your rectangular approximations on that part that dips below the x-axis? Well, if we pick an endpoint, x sub 2, and we draw the rectangle from the x-axis to the graph, now since the graph is below, we have a function value at x2 that is negative. That means basically that your height of the rectangle, since it's oriented kind of going downwards, the height's going to be negative since the function value is negative. And we know when defining integrals and approximations with rectangles, the function value is what determines the height. So what we can see here is those two representative rectangles. One gives a positive area since the rectangle is above the x-axis. The one on the right there that goes below, that has negative area since the function value is negative. So what we're seeing here, depending on how the function is oriented, is we could get positive or negative values for the rectangular areas. If we were to put this together, add up a bunch of them, we could get positive area or negative area. And this is the concept that we'll call net signed area. And if we look at this now as two regions, we have the region above the x-axis, which we'll call a sub 1. There's the region then below the x-axis, which we'll call a sub 2. And we're going to define the net signed area basically as the general answer to how we'll interpret the definite integral. Earlier, we said the definite integral represented the exact area beneath the graph or between the graph and the x-axis. And at the time, the functions and their graphs that we looked at were entirely above the x-axis. To be more general, in this case, if the function goes below the x-axis, we have to account for that, and we basically define now the definite integral as this, the area above a sub 1 minus the area below a sub 2. So we think of a sub 1 and a sub 2 as being positive area. We look at them as maybe geometric figures that we're familiar with. And then since we have a sub 2 below, we subtract that. Now this concept of net signed area can give three possible values, just like usual kind of net change ideas. You could get an overall positive answer, which basically means your function over that interval has more area above than below the x-axis. It is possible if the size of A1 and A2 are equal, you could get a 0 value for the definite integral. And that means basically there's as much area above as below the x-axis. And there is the possibility to get a negative value for the definite integral through this concept of net signed area if there's more area below the x-axis than above. So kind of all possibilities there, positive, 0, or negative, are possible for answers to definite integrals. Earlier, since the graph was above the x-axis strictly, we only got positive answers for the definite integral, since your basic concepts of area make sense for kind of positive widths and lengths leading to positive area. All right, let's go ahead and kind of get into some more. Let's look at a kind of a simple example here. This is a good one to motivate defining the idea of net signed area. Let's suppose we were considering the graph of sine of x. Let's just focus on the interval from 0 to 2 pi. Since all of you are experts in all things pre-calculus where trig functions were introduced, you remember your basic graph of sine of x. It has a period of 2 pi radians. So over that distance from 0 to 2 pi, the graph will repeat. And then it has an amplitude of 1 unit. So the graph stays between the horizontal lines, y equals positive 1 and y equals negative 1. All right, and if we were just to split that period from 0 to 2 pi into 4 pieces, since we have 4 quadrants, you have the intervals from 0 to pi over 2, pi over 2 to pi, pi to 3 pi over 2, and 3 pi over 2 to 2 pi. Those are your 4 quadrants. Just plot your basic sine values going around the unit circle, and you get this graph. Okay, now we can tie this in to what we've been talking about with net signed area. This is a pretty good sketch by hand for the graph of sine. And let's suppose now you were asked to evaluate the definite integral of sine of x from 0 to 2 pi. Now, over the interval 0 to 2 pi, sine of x goes below the x-axis. So we can't think now of the definite integral as being the area beneath the graph, since that kind of gets screwed up if we think of the graph being below, what's below that graph on the negative portion. The alternate approach is to interpret the definite integral as net signed area. And while we currently can't answer what is the area individually of A1 and A2, pretty easy to see from a rough sketch like I have here that the size of A1 and A2 are equal. Now, since there's basically regions above and below, net signed area, the interpretation says we should subtract A1, and then from that subtract A2, the area below. Since A1 and A2 are equal in size, they have equal area, just their orientation above or below is different. That basically is going to add or subtract to 0. And that is because the graph of sine has equal area above and below with respect to its graph in the x-axis over that interval 0 to 2 pi. All right, now what we're going to see later in the course, we don't have all the tools yet available. What is the area, maybe perhaps, just of basically the interval from 0 to pi? So what is the area of that region, A sub 1? We'll be able to answer that shortly, but we don't have all the tools yet. All right, so we'll come back to that in one of our last lectures. What I want to look at next are some properties of now the definite integral, kind of like when we defined limits and derivatives. Limits and derivatives have some properties. Now, we really don't have to talk about derivatives separate from limits, since derivatives are limits. So let's think back first, earlier in the course, when we first introduced what we might have called the limit laws. And it basically says if we have a constant multiple, so a constant multiplying a function, where we have two functions, f and g of x, that we're adding or subtracting, we have kind of some simple rules that relate to evaluating their limits. The first one, you can pull constant multiples in front of the limit. And the second rule says you can add or subtract, take a sum or difference of your individual limits, provided each limit exists. All right, now those limit laws were used to get these now properties of the derivative. You can pull a constant multiple in front of the derivative, and if you have the derivative of a sum or difference, that's equal to the sum or difference of the individual derivatives. Now, derivatives are central to differential calculus. What we're defining and learning about now, the definite integral, that's central to integral calculus. And in fact, you're going to see that through the first part of Calculus 2. Now, why are we mentioning these properties of limits and derivatives? Well, since we already saw earlier, definite integrals are defined as limits. Since derivatives have these similar properties, you might kind of suspect, do integrals have similar properties? They do, because integrals, definite integrals, are defined as limits. All right, so it shouldn't be a surprise that there's a few properties for now the definite integral. All right, the first one here is rather simple. It basically says if we have the integral of a constant function, so the f of x here is a constant c, then we can interpret this definite integral as basically a simple rectangular area. The height c times the length b minus a. Now, why does this make sense? Well, think of what the graph of a constant function looks like. Let's say you were to ask to sketch the curve y equals c, where c is a number. Y equals a number, that's the graph of a horizontal line. So we have some horizontal line, the y value is c, and the interval a to b gives you a base length of b minus a. That's a rectangular area. Multiply the length b minus a by the height c, and we get this value for the definite integral. All right, this is basically the integral for a constant function. The similar properties to limits and derivatives above translate now to these second and third properties for the definite integral. Constant multiples inside the integral can be pulled out front. And in property 3, the definite integral of a sum or difference of functions equals the definite integral added or subtracted to the other function's definite integral. Again, very similar to the above limit property and derivative property. There was a kind of a fourth property here that's not equivalent to properties of limits or derivatives, since we talk about a definite integral for a function over an interval. This fourth property says something about interchanging or switching the limits of the integral, basically reversing your left and right endpoints. So it's written as the integral from b to a of a function equals now the negative, and we reverse the limits. Instead of having it from b to a, we have it from a to b. Now, where does this negative come from? This is not made up. Well, let's look at the interval from a to b, written in red there. Now, the way we define the length of an interval, it is the right endpoint minus the left. So the length of the interval from a to b is b minus a. Now, the property of integrals written there in property 4, the left portion of that has an interval from b to a. Now, what's that length? Well, it's the right endpoint minus the left. The length of the interval from b to a is a minus b. And if you rewrite that, factor out a negative, you can rewrite a minus b as negative, that's where it comes from, b minus a. All right, so basically this says, again, if you reverse the values of your left and right endpoints or reverse the limits of integration, you kind of introduce an extra negative. All right, there's a fifth property, again, unlike any of those for limits or derivatives, since derivatives were thought of as, let's say, coming from slopes of tangent lines. Here, definite integrals, something different area. All right, what this fifth property says is, let's say we have an interval from A to B, and in between A and B is some intermediate x value, C. What this fifth property basically says is you can take the entire interval from A to B and split it into two intervals, an interval from A to C, and then another interval from C to B. So instead of thinking here, the definite integral, the sketch we have, the graph is above, instead of thinking of the interpretation as area beneath that graph as that larger region from A to B, you can split it up into the integral, area beneath the graph from A to C, and then add to that the area beneath the graph from C to B. We'll see this in action in an example that follows momentarily. Let's take a look at one last property. This one's a little peculiar. It's basically saying if we have the definite integral for a function from a number a to itself, a. And this actually, as it turns out, comes out to equal 0. Now, why does that make sense? Well, we interpret a definite integral basically for a function over an interval. And our interval here is a little peculiar. The interval from A to A contains a single point. The length of that interval, the length or width of a single mathematical point is 0. A point has no length or width to it, no real dimensions. So the length of that interval from A to A is 0. Basically, there is no area beneath the graph of a function over a single point. The width is 0. All right, we're going to see some examples in this lecture and then in kind of homework questions that ask you to apply these properties. If you continue into Calculus 2 and beyond, you'll start to incorporate and become very familiar with some of these properties when they're used in kind of solving some problems. All right, let's take a look at our final example for this lecture. Example 3 is a two-part one here. This is an example to maybe just give you a chance to get a sense for what those properties of the integral are used for. And it gives you 3 integrals. All right, the question supposes that for a function f of x, the integral from -1 to 5 of that function f is 2. Another function g of x has an integral from -1 to 5. That integral equals 20. And then for that same function g of x, the integral from -1 to 3 equals 13. Now with those 3 pieces of information, those 3 definite integrals, the question then asks you to find 2 other definite integrals related to those combinations of functions f of x and g of x. Now, maybe pause the video to make an attempt at this. Definitely refer to the properties of the integrals that we just mentioned, those 6 properties. You might want to have them in front of you as you're making an attempt on these, since the question doesn't say really which properties to use. So pause the video and we'll check in a few minutes. Otherwise, just continue if you kind of feel completely lost. But definitely refer to those properties of integrals and see how they might factor into the different integrals you're given here. Take a look at the x values, -1 to 5, -1 to 3, and then in part B, an integral from 3 to 5. We'll check in a few minutes. All right, welcome back. Part A is definitely the most straightforward of these two examples. Basically, part A, since you are multiplying f and g by constants 2 and 3, and then you're summing, is basically asking you to use property 2 and 3 of integrals, the constant multiple property and then the sum and difference property. So what we can do is take this complicated integral, it's kind of made out of several pieces. You can split it into the sum of two integrals involving 2f of x and 3g of x. And then you can pull the constants 2 and 3 out in front of the integral signs. Now the benefit of using this property is you take your current problem, part A, and relate it to your given information. You were given the integral for f from -1 to 5. That's equal to, from what we're told. And then we're also given the integral of g from -1 to 5, which equals 20. If you just kind of plug those values in, you get 2 times 2 plus 3 times 20. I think that comes out to 64. So part A, pretty straightforward application of the constant multiple and sum difference rule for integrals. All right, now part B is probably a little more challenging. Take a look at your information. You're given integrals for g of x from -1 to 5, and you're also told the integral of g of x from -1 to 3. Part B is asking you for the integral from 3 to 5. Now, what does that maybe sound like? We have a larger interval from -1 to 5, and then 3 is in between. It's an intermediate point between x equals -1 and x equals 5. This is asking us to basically split up the interval from -1 to 5 into two intervals, -1 to 3, and then the interval from 3 to 5. This leads us to splitting the integral of g of x from -1 to 5 into the integrals of g of x from -1 to 3, and added to that the integral of g from 3 to 5. All right, again, I'm taking my time to properly enunciate interval and integral. Very easy to confuse that, as I know from in-class experiences. So basically, we're just applying that intermediate property, and take a look, the upper limit, 3, matches the lower limit of the other integral. So as long as they match, you can kind of split it apart and combine them back together. Now, this gives us a way to relate our given information. We're given the integral on the left from -1 to 5, that integral of g of x equals 20, from what we're told. And then the first integral on the right side of g of x from -1 to 3, we're told equals 13. Now, we don't have to do any calculations other than basic subtraction here. Again, we don't have any shortcuts yet for evaluating integrals, but we do have some properties of integrals. Here we get a very simple equation. We just can solve that for what we're asked to find, the integral of g of x from 3 to 5. Again, the concepts are very complicated here since they're new, but the underlying calculations really are really simple, just subtraction here. So we get the value for the integral from 3 to 5, just subtracting, and it comes out to 20 minus 13, which is 7. Again, it's the concepts that are complicated right now, not the calculations, since we're transitioning to a new part of calculus, integral calculus. All right, so that's pretty much the end of this lecture on definite integrals, but there's some little ends I want to wrap up since we are in a mathematics course. What I want to close with is, since we gave a technical definition for definite integrals as a limit. Again, we don't use that in practice. We don't evaluate the limit as the number of rectangles goes to infinity and then sum up an infinite amount of rectangular areas. That's highly impractical. But we do want to know, thinking back to the limit definition of derivatives, well, some limits don't exist. And with what we saw with the idea of differentiability, some functions aren't differentiable. Some functions and their graphs have sharp points and various discontinuities. So what I'm doing right now is trying to set up the expectation maybe something similar happens for integrals. Do all definite integrals exist? Are there times where they do not exist? This kind of gets you on the path to kind of more technical, higher level mathematics where proofs come in. We're not going to touch on that in this course, but the foundations of it are introduced right now. All right, so earlier we gave the idea of what it meant for a function to be differentiable, which intuitively or basically meant smooth. Now we're going to ask, when is a function integrable? In other words, when does the definite integral of a function exist? Now, I don't want to kind of go into too much detail, since this is more properly left, in my opinion, for higher level mathematics course, but I do want to build that foundation. Earlier in this lecture, we defined the definite integral as a limit. The limit as n, the number of rectangles, goes to infinity. For what we have expressed here, what we said was the right endpoint approximation with n rectangles. Now, what this idea of integrable is asking is, for which functions f of x does this limit exist? It's a really cumbersome limit of this finite sum of n rectangular areas, but hopefully you can see where the existence ideas come in. So when we ask which functions are integrable, they're basically asking us which functions have this limit definition, for which functions does that limit definition exist. All right, as it turns out, there's a really simple theorem, which is very broad. And the theorem basically says, if the function that we're interested in working with is continuous on an interval, a to b, then it is also integrable on that same interval. And basically what that says is, if we have a continuous function, the definite integral exists. And the good news is, a lot of functions that you'll encounter in your standard calculus sequence and in some of your science and engineering courses, most of them are continuous. Powers of x, polynomials, exponentials, logs, trig functions, most functions are continuous. So pretty much, this theorem says most functions that you'll encounter are integrable. Now, most functions you encounter are integral, but not all. There are some problems. This theorem says the function has to be continuous. Now, as it turns out, there are other functions that are integrable but not continuous. And I want to put you on the path maybe to higher level mathematics. Maybe you're going that route, but probably not. One case for a function that is not continuous, but it is integrable, is for a piecewise defined function. Again, as maybe were introduced in your pre-calculus course. And provided it is a piecewise defined function with a finite number of jump discontinuities. All right, so that example there of that piecewise defined function with 3 different jump discontinuities, this would be integrable. We're not going to prove that, but as long as there's a finite number of jump discontinuities in your piecewise defined function, the definite integral as we defined it exists. Okay, well, just to put you on the path maybe to what comes after the standard calculus sequence, in case you're interested, let's consider a somewhat bizarre function. Let's say we consider the function f of x, where it has the value 1 if the input x is a rational number or fraction. And that function, if you plug in an x value that is irrational, in other words, a number that can't be expressed as a fraction, then it returns the value 0. So just two examples. If we were to plug 2 into that function, since 2 is a rational number or fraction, 2 over 1, that would return the value 1, since 2 is rational. A standard irrational number, pi, that can't be expressed as a fraction. When you plug that value in for x, pi, to this function, the function returns the value 0. Now, this is a weird function, but it does put you on the path to higher level mathematics. I'm not going to answer it within this lecture, but go forth in case you're interested. As we have it defined here, is this function integrable on the interval from 0 to 1? If you're curious, this is called the Dirichlet function. Take a look on Wikipedia, perhaps, and see what you can find out.